So in this video, we're going to look at constructive and destructive interference, a little bit more detail. So for two monochromatic, so that's two single frequency sources of light in phase, then the waves at some point in the distance in a vacuum, they're going to constructively interfere when the difference between the two waves, so path difference just means the difference between the two waves, is an integer number of wavelengths apart. I'll show you what I mean by this in a second. And they're going to destructively interfere if the path difference between the two waves is half a wavelength integer apart. So what I mean by that is the following. So here we have a diagram. Now we have two light sources, okay? Now they're single frequency, they're monochromatic sources of light. So single frequency, which means they're going to have the same wavelength. So light has been illuminated from these two slits and they're going to travel the exact same distance. So therefore what's going to occur at this point on this screen over here is that they're going to each have traveled the same distance, and what's going to happen is that their two crests are going to meet, and what we're going to see is we're going to have a bright light or constructive interference because both these waves have traveled an equal distance, and therefore they have a path difference of 0, and it's going to result in constructive interference on the screen. In our next example, we have again the two sources of monochromatic light. However, now what's happening is this bottom one is traveling a longer distance, okay? Now, in order for constructive interference to occur, it needs to travel one full wavelength extra, and if it travels one full wavelength extra, then the two crests are still going to meet and result in constructive interference, or high amplitude, which is going to result in a bright light. And the same would be true if we change the angle even more and they were meeting here. So, argument's sake, if the angle was altered slightly, and then this one traveled to here, and this one traveled, instead of one extra wavelength, if it traveled 2 extra wavelengths, then when it met at this point here, it would still result in constructive interference, because if the path difference, okay, is an integer wavelength, so if it's 1 wavelength or 2 wavelengths or 3 wavelengths, it's still going to result in constructive interference. So to summarize, so if you have two monochromatic sources of light, so single frequency and hence wavelength, then the waves at a point will constructively interfere when the path difference from the two sources is a integer wavelength. So m, where m is an integer wavelength, so 1, 2, 3, 4, etc. That's going to result in constructive interference. Similarly, if we have, in this case here, what we have is now the path difference between these two light sources is now half a wavelength. So they're half a wavelength difference, so it's only half a wavelength. And when they meet at this point on the screen, so that's traveling that much, and this is traveling half a wavelength extra, what you'll notice is that the peak and the trough are going to meet when they hit the screen, and it's going to result in them cancelling each other out, and no light is going to be seen at this point, or destructive interference. Later on, we'll look at this idea in Young's double slit, but for now, all I want you to know is that if you have two monochromatic light sources, and if they travel a path difference of half a wavelength, so whether that's 1/2 of a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, or 3.5, etc., it's going to result in destructive interference because the path difference between the two light sources is half an integer wavelength, and then it's going to result in peaks, crests and troughs cancelling each other out, and destructive interference. Now here we have two sources of light. Now the crests and so the dark lines are the crests of the wavelength, and the thinner lines are the troughs. So basically, these two light sources here. So let's just pick this red. Let's pick. What are we going to pick? 1, 2. Yeah, no, let's pick this red point here. So if we look at our source 1, this here is the crest of the source. Here is another crest. So this is sort of like one wavelength, 2 wavelengths away, this point here. And here is 1 wavelength, 2 wavelengths here. So the path difference, or M, is 0. So here, these two crests are going to meet. It's going to be constructive interference. And anywhere along this line is also going to be constructive interference, because we have crest and crest meeting here, crest and crest meeting here, crest and crest meeting here. But we also have troughs, because remember these are the troughs. Troughs and troughs meeting here, troughs and troughs meeting here, etc. So all along this line, everywhere where these two light sources meet have a path difference of 0. So the path difference of 0, so all along this line is going to be constructive interference. Likewise, let's just pick this point here. So here it's 1, 2, and let's actually draw it so we can see. So we've got 1, 2, 3 crests away from this wave source, and this one's 1, 2, 3, 4. So there's one integer wavelength difference at this point here in 2D. So it's still going to be constructive interference because the path difference is 1. And you can pick any point along here, and it's going to have a path difference of 1. Any point along here, it's going to be a path difference of 2 between the two light sources, and so on and so forth. Let's pick this point here. And here, if we have a crest 1, 2, 3, so it's 3 wavelengths away. And if we go to this source, so it's 1, 2, 3.5 wavelengths, because it's a trough. So it's going to have a path difference of 3 and 3.5, so a path difference of a half. And because we have a crest and a trough meeting, it's going to result in destructive interference. So whenever you have a path difference of half, or 1.5, 2.5, etc., it's going to result in destructive interference. So just to recap, when you have two monochromatic light sources, when the path difference is an integer wavelength, it's going to be constructive interference. And when you have monochromatic sources in phase, when there is a half integer wavelength apart, then it's going to result in destructive interference. This is in 1D, and this is in 2D. Now, I'm going to do this question, and I'm going to get you to do this past exam question yourself. So in this question here, so in this one here, the spacing between the waves represents 1 wavelength. So we can just think of these bolded lines as troughs. As crests. So these are crests, and that's 1 total wavelength. So determine the path difference between the waves at the different points and whether the waves will constructively or destructively interfere. So at point D, let's just start with point D. So imagine that's sort of, these are wave fronts. So if that's 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, and this is 1, 2, 3, 4. So again, here, it's going to have a path difference of 0. So the path difference here will be 0, which means it's going to result in constructive interference. At point C, it's also going to have a path difference of 0, because it's 1, 2, 3, 4, 5, 6 wavelengths, 1, 2, 3, 4, 5, 6 wavelengths. So it's going to be a path difference of 0, and it's going to result in constructive interference. Again, at point E, it's going to be 1, 2, 3, 4, 5, 6 wavelengths, and 1, 2, 3, 4, 5, 6, 7, 8. So 6 and 8, so it's going to be a path difference of 2 wavelengths, and it's also going to result in constructive interference. Now, A and B is a bit trickier. Now, point A, so from source 1, okay, this is 1, 2, 3, 4 wavelengths away. And from source 2, it is 1, 2, 3, 4, 5, 6.5. So it's going to be, what did I say, 1, 2, 3, 4. So it's a path difference of 2.5 wavelengths, which means it's going to result in destructive interference at this point here. And let's look at point B. So at point B from source 1, it's 1, 2, 3, 4. So it's 1, 2, 3, 4, 5.5 from source 1. And for source 2, it's 1, 2, 3, 4, 5, 6.5. So if it's 5.5 and 6.5, it's going to have a path difference of 1. So it's going to result in constructive interference. So whenever the path difference is integer wavelengths, it's going to be constructive interference. And whenever it's half wavelengths away, it's going to result in destructive interference. Now, these 2D questions are very rare. The one in the textbook I really don't like, so I found you this old past exam question. So what I want you to do is to pause it, read it, and have a go at it. And then so have a go at it. Alright, so now I'm going to go through this question. So we have 2 transmitters of radio waves with a frequency of 136 kilohertz, and they're separated by some distance, 8.8 kilometers. So the radio waves emitted in phase, so they're in phase by these transmitters as shown in the diagram below. The spacing between the lines represents 1 wavelength. State whether the radio waves from the 2 transmitters undergo constructive or destructive interference at point P. So if we first look at the one on the left, it's travelled 1 wavelength, 2 wavelengths, 3 wavelengths to point P. And if we look at this one here, it's travelled 1, 2, 3, 4. So the path difference, if this has travelled 3 wavelengths and this has travelled 4 wavelengths, the path difference between the 2 sources to point P is 1 wavelength. So if the path difference is 1 wavelength, it's going to result in constructive interference. So state whether the radio waves from the 2 transmitters undergo constructive or destructive interference at point P. Give a reason for your answer. So constructive interference because the the waves have a path difference of 1 wavelength. And it's not letting me write. Alrighty, that's what I wanted to go through in this video. Cheers.